Well, good morning, team. Let's take a look at some more hybridization. So we introduced hybridization in the last video, showed kind of the process of taking s orbitals and p orbitals and hybridizing them. And remember the number one rule: the number of electron groups on the Lewis structure is the number of hybrid orbitals you need. The number of hybrid orbitals you need is the number of atomic orbitals you need to hybridize. Start with the s, then the px, then the py, pz, well, or any order on those, and you're good to go. If you need an expanded octet, which we're doing today, we're going to need some D's, right? sp3df. We'll never need the F's, trust me. So we only looked at sp3 hybridization last time, but it took a while to do that video because we're introducing the concept of hybridization and what a hybridization scheme is. So we don't have to redo that. So let's look at the hybridization for expanded octets today. Sp3d and sp3d2, and we will relate that to Vesper, right? Is that a trigonal bipyramid, octahedral, those kinds of things? And remember, number of electron groups, number of hybrid orbitals, that's the connection. Number of electron groups on your Lewis structure through the Vesper theory, right? Lewis theory will be the number of hybrid orbitals from valence bond method with hybridization. That's the connection between the two. So let's do an example. Let's say, just kind of show it. We'll just take it. We'll take it live, my friends. Let's take AsF4 minus. So we'll introduce a polyatomic ion as well. Hey, you got to do the Lewis structure. It all starts with that because you need to know how many electron groups you have. You have to know that. You can't. There's no way you do the hybridization if you don't know how many electron groups you need, right? So if you do the 6n plus 2, hey, if you can pause it and do it, that'd be great review. But you'll get 6n plus 2 is 32. Number of valence electrons is 34. You end up getting a negative 2. That means you've gotten, remember, from Lewis theory. If you need to review that, go watch that video on Lewis structures. That's an expanded octet by 2. So we're going to have 10 electrons around the central arsenic atom. So put the 4 fluorines around it. That gives you 2, 4, 6, 8. And then we need 2 more because of the expanded octet. Righto, daddy-o. Boop. Got those extra electrons in there. So that gives us 1, 2, 3, 4, 5 electron groups. And remember we need brackets around it to show that we picked up an extra electron and all that fun stuff. So once we have this, we can make that statement that we have 5 electron groups on the arsenic. Everybody agree? 1, 2, 3, 4 single bonds, 1 lone pair. That's 5 electron groups, which means we need 5 hybrid orbitals from 5 atomic orbitals. S, px, py, pz. We need one more. We need one of the d's. It doesn't really matter which one of the d's. We'll just say we need a d. Remember the 4-leaf clover things? Let's draw that on the next board. And then we'll do a simplified version of sp3d2. Let's see if we can walk through this together live. It's the same for all hybridization. It's the same thinking process. Start with the Lewis structure. Count the electron groups. 5 electron groups. Remember the rule? That means we need 5 hybrid orbitals. Same number. Don't overthink it. Too many people overthink chemistry. Right? To get 5 hybrid orbitals, we need to hybridize 5 atomic orbitals. All right, so we need 5 atomic orbitals. So let's take a look at that code. So we need an S. That's 1. We need a P. Let's call that the PX. That'd be 2. We need let's call that the PZ. It's pointing up and down, depending on how, all we have to do is just rotate it, and it doesn't make a difference. Let's call that the PZ. Let's call that the PX. Let's call this the X direction, Z direction. Y's coming at your face. That's impossible to draw, so we'll do it this way. 1, 2, 3, 4. I'm really oversimplifying this from what I did last time. But that's only 4, so we need 1 more S, right? So 1, 2, 3, 4. Whoa, we need 1 more. Let's do a d orbital. That's a pretty ugly looking d orbital. So that could be the dxz, dyz, dxy, whatever, dx squared minus y squared. That, my friends, would be sp3d hybridization. So I'm not going to go through what I did last time and show all of these atomic orbitals and what the hybrid orbitals look like, but let's look at the overall structure for that. We'll do that on the next board. So we're going to combine all these. Let's look at the resulting structure. It's going to look something like this. Does that look familiar? You've got a little triangle in the equatorial part with the axial part. That look like a trigonal bipyramid to you? Yes, 5 electron groups from Vespers, trigonal bipyramid. Let's draw that on the next board. See, now, I'm not going to ever ask you to draw this, right? All I want you to do is go, hey, there's 5, Sp3d. Boom. You don't have to label them. Let's look at what this looks like in 3 dimensions. So with 5 electron groups, 1, 2, 3, 4, 5. 5 hybrid orbitals needed, 5 atomic orbitals, Sp3d. So we've got Sp3d hybridization, and that is the structure. You're going to get 1 up, 1 down, and then kind of a triangle in the middle. Hard to see in 3 dimensions. It's better with a dash wedge structure, but this is what the structure would look like with hybridization theory from the valence bond method. And then if we relate that to Vesper, this would be 5 electron groups are trigonal bipyramid. You have 90-degree bond angles there, 120-degree bond angles there. So there's our axial positions. Here's our equatorial, so you can see the 90-degree bond angle there. And in the equatorial, you can see the 120. All right. So let's draw that. So we've got the 90 degrees here. 120 there. That's the connection between Vesper and hybrid. They match, right? Which is really, really nice. And then we'll show the overlapping in a whole different thing. We're going to do these orbital overlap diagrams that are really cool. We'll show the fluorine orbitals come in and overlap with that. We'll do that in another video. I just want to look at the hybridization. Let's do the hybridization scheme. I love that word, scheme, for this. We're going to need another board. You guys ready to do a hybrid? That didn't come out right. So much for my weird accent. Hybridization scheme. So again, you're doing like an orbital box diagram electron configuration, but instead of left to right, you're going bottom to top. You're going vertical instead of horizontal. Now this is where a lot of students make a mistake when there's an expanded octet. So remember, you look at arsenic. We're doing the valence orbitals, right? It's the valence bond method. So arsenic's over here. Where did arsenic go? Here it is. So 1, 2, 3, 4. Okay. So it's the 4s4p. So there's the 4s4p, but now we got a D. A lot of students want to take, because arsenic's here, they want to take the 3D. But see, the 3D's filled. We got to go for the next lowest energy empty orbitals. 4D is empty, 3D's filled. If we took 3D, you'd have 10 electrons in there, and you'd have a big glut of electron. Right? It'd be way too crazy. You need, if you want to make a note, you need the empty one. So it's always the same numbers. If you need the D, it'll be 4, like 4s4p 4D, 5s 5p 5D. It has to be. So they have to be the same. You need empty ones. So now let's put the electrons in there for arsenic. Okay, so if you look at the valence electrons for arsenic, arsenic is right there with the pnictogens in 5A. So it's got 5 valence electrons. And I'm going to show you there's something we have to watch out for. Let's see if you know it. Something you have to watch out for. Hint. All right, here we go. So the 4s is filled. So 1, 2, 3, 4, 5. Right? There's the 5 valence electrons that for the free. This is the arsenic atom before it hybridizes. Right? That's the free arsenic atom. But we have a negative charge there. That means we have an extra electron. See that right there? That's an extra electron from the charge. Now remember again, the whole point of the hybridization scheme is once we hybridize it, it should predict the Lewis structure. It should predict the 4 single bonds and the lone pair. And again, there's terminology we use where a single bond is a sigma bond. We're going to really hit those a little harder later. So I'm going to bring that extra electron, and I'm going to put it right there. Boop. If you forget that extra electron, as they say in Minnesota, you're toast. here we go. So now we got a total of 6 electrons. Now remember, we're doing sp3d hybridization. So we need all the S, all the P's, and 1 of the D's. Everybody agree? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. sp3d. So I circled 1, 2, 3, 4, 5 orbitals. 5 atomic orbitals gives you 5 hybrid orbitals. So I'm going to draw 5 here. And these are my sp3d hybrid orbitals. I got a D in penmanship. All right, here we go. That didn't stop me. So 5 boxes, 5 boxes. Now, how many electrons did I circle? 1, 2, 3, 4, 5, 6. Correct? So let's draw those 6 electrons in it. 1, 2, 3, 4, 5. Remember Hund's rule. And then that extra electron for 6 goes there. If we didn't account for that, we would predict 5 single or sigma bonds. That's not what we have. That extra electron goes there. But there's 4 of the 40 orbitals we didn't use. Remember, you don't carry the number over. That hybrids don't have like a 2, 3, or 4. So those are going to carry over. And I have 4. And now remember, the hybrid is an average energy of the S, the P's, and the D's. So it's 3 part P, 1 part D, and 1 part S. So as long as you draw them above the S and below the D, I'm pretty good. We'll wait till PChem or something where you want to get the ratios a little bit better. We're going to have 4 empty D orbitals. So those carry over unhybridized. So you need to draw those, and they don't change in energy. They're not hybridized, so they stay at the same height there. Okay? So this is the hybridization scheme for sp3d. What does this predict? Let's take a look at it. Remember, when you have 2 electrons in a hybrid orbital, that predicts 1 lone pair or 1 non-bonding pair. Oh, right there. And if you have a single electron in, that predicts a single or sigma bond. Or what we call sigma. And I will be defining sigma bonds when we start to get into double and triple bonds. I'm going to start to talk about sigma and pi bonds in a little while. So do you see that? 1, 2, 3, 4 single bonds or sigma bonds and 1 lone pair. So that matches the Lewis structure. That's what I'm going to be looking for on quizzes and tests, my friends. I'm going to make sure that your Lewis structure makes sense based on the hybridization scheme. They should relate. If something's off, either your Lewis structure is wrong or your hybridization scheme is wrong. Like you might have forgot that electron. If you forgot the electron, you'd predict 5 sigma bonds or 5 single bonds. That doesn't match. So think about it. Now, are there some that don't work? Heck yeah. Resonance, things like that. It's not a perfect theory. We need molecular orbital theory for that later on down the road. But for my quizzes and my exams, they'll always match, all right? Hey, there you go. That's the hybridization scheme. Let me write that down real quick. Hybrid, that's a long word, gang. Hybridization scheme, remember? That's the hybridization scheme. It's a little better than drawing all the orbitals and things like that. So let's look at sp3d2 real quick, just kind of a fictitious sp3d2, and show you how the hybridization works. Almost done with this. Let's do some sp3d2, prototypical example, sulfur hexafluoride. I think we've looked at that one before for Lewis structures. So if you do your 6n plus 2 minus number of valence electrons, 44 minus 48 is negative 4, expanded octet by 4, that'll be 12 electrons around that sulfur atom. So you get the 1, 2, 3, 4, 5, 6, 2, 4, 6, 8, 10, 12 electrons, complete the octets. So when we look at this, here we go, you ready? We've got 6 electron groups on the sulfur atom. Everybody agree? 1, 2, 3, 4, 5, 6 single bonds. So that's 6 locations where we have electrons. How many hybrid orbitals? 6. Haha, it's the same number. So we need 6 hybrid orbitals. In order to get 6 hybrid orbitals, how many atomic orbitals do we need to hybridize? 6! This is the evil one. So we need 6. I'm running out of room here. 6 atomic orbitals. 6 atomic orbitals. You ready? S plus P plus P plus P, that's 4. Plus D is 5. Plus D is 6. So that's Sp3 D2. So I'm not going to show the orbitals for this one, the spherical S, the 3 P's, PX, and then the 2 D's. I'm not going to show that. So you've got 1, 2, 3, 4, 5, 6 Sp3d2. You need those 2d orbitals, empty d orbitals, not filled d orbitals, for the expanded octet. Let's look at a hybridization scheme for that, shall we? And that should match this. Let's do it. Do it ahead of time if you can. Take the sulfur atom, right? Remember, take the unhybridized sulfur atom, do the vertical orbital box diagram. It's not charged, so you don't have to worry about extra electrons or anything like that. Hybridize it and see if that matches. See if it predicts a 6 single or sigma bonds for me. Did you get this far? Did you? So I redrew the Lewis structure over there. Remember, what we predict from this hybridization scheme has to predict that Lewis structure. So here's the sulfur atom. So if you look at sulfur on your trusty dusty periodic table, don't leave home without it. Right there, N equals 1, 2, 3. So that's in the 3rd energy level. So we need the 3s and the 3p. And remember, we're taking the next, there is no 2d, correct? So you need the next highest empty energy level for D, the sublevel. Now, sulfur is in group 6A with the chalcogens, right? So it's got 6 valence electrons. There's no charge on the species, so we don't have to worry about that. Let's put the 6 valence electrons in there. Are you ready? You ready? 1, 2, 3, 4, 5, 6. Remember, there's no electrons in the D. There shouldn't be, at least for the ones we're going to deal with this class. Now, we're doing Sp3d, correct? Sp3d2. Sp3d2, right? 6 electron groups, 6 hybrid orbitals, 6 atomic orbitals. Sp3d, D. D, that's 6. So we need to circle 6 of these puppies. 1, always go from the lowest energy. 1, 2, 3, 4, and then take any of those 2. I'll just take the first 2, right? Not a big deal. So I need the S, I need the 3s, the 3p, and 2 of those 3d. That leaves me 3 of the 3d orbitals that I didn't use. So they're just going to carry over, right? So let's redraw those. So we never touched those 3ds. So they're going to stay exactly at the same energy level. Now the hybrid orbitals will be 3 parts P, 2 parts D, and 1 part S. So it's going to be up a little bit higher. So let's make sure they're in between. And that's 1, 2, 3, 4, 5, 6 boxes, 6 atomic orbitals. So we're going to get 6 hybrids. One, 2, 3, 4, 5, 6. So those are our 6 hybrid orbitals. And those are our Sp3 D2 hybrids or hybrid orbitals. So far, so good, right? We circled 1, 2, 3, 4, 5, 6 total electrons. They're going to carry over into the hybrids. So let's put the 6 here, right? There's none in there. They don't go up there. So 1, 2, 3. And you old enough to remember that commercial with a little owl and the lollipop? A 1, a 2, a 3. Anyway, it just entered my brain. 1, 2, 3, 4, 5, 6. The power of commercials. All right, so there's nothing up there. There's nothing filled, so this does not predict any lone pairs, right? You'd have to have the 2 electrons in there. So we've got 6 orbitals, hybrid orbitals, with an unpaired electron. So that predicts 6 single, or what we call sigma, we're going to look at single and double bonds differently in hybridization theory. That's going to really hit in the next video hard. All right, so we predict 6 single or sigma bonds. Does that match? 1, 2, 3, 4, 5, 6. That is a match, my friends. Exclamation points optional. I love hybridization schemes. They're so logical. Just watch out for if it has a charge. That'll mess you up if you forget it. And there you go. All right. So we've got a couple other ways of looking at this. We're going to look at SP and SP2 in the next video, hybridization, because that's how we're going to deal with multiple bonds, double and triple bonds. And then we're going to look at a whole different viewpoint. Instead of looking at the hybridization scheme, we're going to look at orbital overlap diagrams, where it's just like Valence bond method. We actually watch, we're going to draw the orbitals. It's like big old, you ever gone to a party and people do the little animal balloons? It literally looks like those. It gives you the most detailed view of it, but it just covers your whole page, and it's just like these little animal balloons all over the place. It's pretty cool. And then we're going to look at some other kinds of diagrams that are a simplified version of that, which work a little bit better. So there you go. That's for expanded octets, Sp3d and Sp3d2 hybridization with their corresponding hybridization schemes. Let's do Sp and Sp2 in the next video. You guys are awesome.